So, oh, that's very bright. There, that should be better. So I am going to go through Lecture 5.1, and this is a sort of warm-up for the lab exercise this week. So we're going to be doing this week AC to DC conversion. So take an AC signal and convert it to a DC signal, something that is very useful for doing things like charging cell phones. Well, that's all that matters anyway, so yeah, and other DC applications. All batteries charged with DC, well, all that I know of, charged with DC power, so yeah. It's a really useful thing to be able to do, and it's actually not that hard to do on sort of quick and dirty, and understanding how it works is a useful thing. And doing the circuit analysis for a circuit with 4 diodes is a bit of a challenge, so I thought I would introduce that analysis in this lecture. So, in lab exercise 5, we will build and measure the response of a diode full wave bridge rectifier circuit. It's a mouthful, but a full wave bridge rectifier circuit. This lecture is intended to introduce the circuit used to convert AC signals to DC signals. Figure 5.1 shows a circuit diagram for a full wave bridge rectifier. 4 diodes perform the rectification. A capacitor in parallel with the load effectively smooths the rectified signal. So this is what we're looking at here. We've got a source. I included a source output resistance because we will be using the function generators, which have an output impedance that needs to be taken into account because they're unregulated sources, as you guys saw in the last lab exercise. And we've got 4 diodes, and they're in this sort of cross bridge configuration. And then you have the output voltage that is the same voltage that is across the capacitor and the load resistance. So the capacitor is there to smooth, and so we're going to find that to be the case. We saw in class an example of a half wave bridge or half wave rectifier circuit with a single diode in it. The full wave allows you to get not just clip off that bottom half, but to fold it over and to become the top half. So we're thinking about this as putting in a signal like this and getting out a signal that looks, if there was no capacitor, it would look like a bump and then a bump and then a bump. They should all be the same. I don't know why I can't make any of them the same. Like that. So this is the upper half, and then this would have been down here, but it's flipped, and then this would have been down here. Yeah, etc. Yeah, a lot of little dots. So this is our rectified signal, but if we want to have, so this is all positive now. Okay, so I thought of this as being time, and this is being voltage. VRL, or V out, I guess. Once you put the capacitor in there, though, it's going to smooth this out. The capacitor does something that looks like averaging to this. The idea being that you charge up the capacitor when this thing is charge up the capacitor each time you go through this bump. Okay, and so once you recharge it, it doesn't decay as fast as this input sine decays. So it instead will follow this sort of slower decay in between humps that bring it back up to its nominal value. Okay, and the average of that is our DC value, and whatever is left over in terms of it rippling, as we call it, is called the ripple. Okay, so this is going to be our V DC, the one in the middle, and then the bounds there will be called the ripple. We use the symbol delta V to say this is the ripple. So we're gonna return to that, but that's kind of the idea, like a just high level view of it. Okay, where were we? Yeah. There are 4 diodes, so there are 2 to the 4 possible diode states. 2 times 2 is 4, times 2 is 8, times 2 is 16. I just got lucky that 4 to the 2 is equal to 2 to the 4. So, who knew? This is 2 to the 4. And we'll try to make good guesses and avoid invalid states in our analysis. So like we don't really want to have to go through all of these 16 possible diode states, right? That's a lot. We prefer to make some good choices early that allows us to avoid the ones that aren't going to happen. So let's try that. So analyzing the circuit. Let's begin by thinking about our diode model. Piecewise linear is our go-to. However, we can simplify it even further if we assume the load won't draw much current. The load in lab exercise 5 is 1 kiloohm, so only small currents will flow through these diodes. We're going to put in something like 8 volts max, and it's going to have a load of 1 kiloohm, and so we're talking about very small numbers of milliamps. We could go through the process of determining the current flow and choosing an operating point for diode resistances. But with such small current flow, we'll still be stuck setting all of the diode resistances to 0. So let's just do that now and not go through the whole rigmarole of that. So choose a model to model the circuit as shown in figure 5.2. At this point, we could perform a single analysis of the entire circuit. So let's look at the figure first. So we took each of the diodes and we split them up into an ideal diode and a voltage drop. When you take the resistance to be 0, it effectively turns the resistor into a wire, so all of the diode resistances are just wires now. So we've got our diode 1, diode 2, diode 3, and diode 4. And these will have 0.6 volt drops in them. And yeah, so we can do a full analysis, and that's what I'm going to warn us away from in this case, because it's just going to get really involved up front. Instead, let's try to eliminate possible states by just reasoning our way through. We choose to reason our way through the potential states and analyze the few that survive. Consider the case of Vs being greater than 0. So, in these regions here, where Vs is greater than 0. So during those times, the only potential pathway for current is through D1 and to return through D2. So I didn't label on this diagram here. So this is D1, this is D2. And this is D3, and this is D4. So we've got, what I said was when Vs is positive, the only possible, if it's going to conduct current at all, the only pathway for current to go is going to be through diode 1. Diode 4 is turned in the opposite direction, so it's going to be in reverse bias. It's not going to flow current. So the only possible way is to go through diode 1, but to go through diode 1, it has to have a return path. So if it goes through diode 1, it comes through these guys, great. It's got to come back through D2 or D4. If it goes back through D4, all you've done is just short it out. So that's not one that we're going to consider. So we can eliminate that one as a possibility. D2 here does complete this loop, so that's the only way that this could work if VS is positive. It might be off. It might not be high enough voltage to actually drive to turn these diodes on, but that's the only way it might work. On the other side of the coin, if you look at negative stuff, that's when you're down here, the only possible pathway is going to be, it's not going to go through D2, it's going to go through D3, and it's got to come here and it's got to come back. If it was to come back by D2, once again, you would just be going around the loop. So instead, D4 is the possibility here. So it might return by D4. So you kind of have this like flipping back and forth between those two possibilities. And then there's also going to be some situations where it is off completely. All the diodes are off. Okay, that's also possible. When this voltage isn't high enough, it's not going to be able to turn on these diodes, or low enough in the negative case. So that's kind of what we're working with here. Let's see, what did I say? So similarly, current cannot flow from ground through D3 to the positive side of the capacitor. That is, D1 and D3 cannot both be in forward bias, and neither can D2 and D4. So we can't have 1 and 3 on at the same time. We can't have 2 and 4 on at the same time. Similar consideration, Vs less than 0 shows that current can only flow to the load via D3 and return through D4. So we can either do D1 to D2, or we can do D3 to D4. And then there's also going to be the possibility that they're all off. Furthermore, we cannot have current flow to the load side of the circuit and not return. We've already talked about that. So it leaves only 3 possible states. The primary charge state, S1, we'll call it, when D1 is on and current must return via D2, so it must also be on. D3 and D4 are off, corresponding to figure 5.3. So this is the figure. If we say that the other 2 diodes are off, then this is the circuit that we're left with. In fact, we could just replace D1 and D2 since we said that they're on with wires, but it is kind of nice to remember where they came from. So we're assuming that they're on and they're ideal, so they just act as wires, pure shorts. And this is a relatively simple circuit now. It's just got a resistor. It's a voltage source going through a resistor that then we get another drop in the voltage, and then we get the drop across the capacitor and the resistor. And it flows back. It also has a drop down there. So you've got a relatively simple circuit for this primary charge state. And so that is when we can do it sort of mathematically. We can say D1 is on, D2 is on, D3 and D4 are off. Secondary charge state, S2, is when D3 is on, current must return via D4, so it must be on. D1 and D2 are off, corresponding to figure 5.4. So this is the one down here, so this is the cross one, right? This is also when Vs is negative is the only chance that that's possible. This one only is possible when Vs is positive. So this is our diagram. So when it's negative, it goes, current flows through D3, through the load, and the capacitor charges the capacitor, and then flows in return back to the positive side of the source through RS. So yeah, that's the secondary charge state. Okay, and the third state, S3, is going to be called the discharge state. So when all 4 diodes are off, the charged capacitor discharges into RL, corresponding to figure 5.5. So this is the last figure on this next page, which has them, all of these diodes are off. So the source is completely disconnected from the capacitor and the load, but the capacitor is probably charged at this point. And so if the capacitor is charged, then it's going to flow current into RL by the equation that VRL is equal to RL times RL, Ohm's law for the resistor. So you can find out what this output voltage would be, which is VRL. You could, I mean, there are a lot of ways to cut it, but this problem is actually a lot less involved than the other two. So solving this one also requires a little bit of work. The other two require a bit more work, but they're all pretty reasonable. So I think that was the end of that. Yeah. So let's consider each of these states as they arise from the initial time. Okay, so this is the sort of like going on a ride from time equals 0 and seeing what happens in the circuit. As we do so, we can examine both the conditions that arise or that give rise to each diode state, S1 through S3, and how the circuit behaves during each state. Let's assume the capacitor begins uncharged. This isn't much of a stretch considering that it has a load resistor across it to which it can discharge. So if you have a resistor connected across the capacitor, it's going to discharge into that resistor. It's just a matter of how long it takes to discharge, but for typical values of R and C, it's relatively quickly. So let's also assume Vs increases sinusoidally from 0 volts. So that's what we'll take as our starting input. At first, there's not enough voltage to drop across D1 to turn it on. So we're stuck in the discharge state, S3, until Vs increases enough to overcome both the 0.6 volts associated with diode 1 and the 0.6 volts associated with the return diode, diode 2. So when Vs is greater than 1.2. At that point, we transition to S1. So we start off here because we're increasing the voltage up, but we can't get diode 1, well, the real diode up here. We can't get diode 1 and diode 2 to turn on because they have inside them these 0.6 volts drop. So you have to be able to overcome the 0.6 volt drop on both sides, the return, the forward and the return. So here we see it with the 0.6. You got to be able to overcome this 0.6 and you got to be able to overcome this 0.6 drop. So you have to be greater than 1.2 ohms, sorry, volts, 1.2 volts in order to get to state S1. So that is what we do. As Vs continues to rise, now in state 1, the output voltage is of course equal to the capacitor voltage and the load voltage, and that all of that increases. That is, the capacitor charges. When Vs decreases, the capacitor voltage doesn't immediately disappear, since its discharge into RL is typically relatively slow. As the decrease in Vs continues, it will switch back to state S3, but this time before reaching 1.2, because now the capacitor is still charged, right? It has been slowly discharging, so slowly discharging, but it's been charged up. Remember the first time we transitioned from S3 to S1, we had to get above 1.2 volts. But now things have changed a little bit. We need to get, once we get down to 1.2 volts plus V out, that's the, if you look at the loop here, now there's a voltage at V out, right? So now it's not just overcoming this, it used to be 0 on V out, but now we got to overcome not just the 0.6 and the 0.6 volt to flow current to it. We also have to overcome this voltage as well. So that's another thing that comes in. So that leaves us in right. As the decrease in Vs continues, it will switch back to state S3, but this time before reaching 1.2 volts, because now the capacitor is still charged, although it is slowly discharging. Reconsidering the S3, we see that Vs being greater than 1.2 plus V naught, or V out, for the diodes to be on. That's the condition. So we have now discovered an alternative formulation of S1. Instead of telling you the diode states, we can tell you now that we're in those diode states when Vs is greater than 1.2 plus V out. So let's consider development of output voltage during S1. In this state, we can analyze the circuit as follows. Here are the elemental equations. So this is, while it's charging up the capacitor, these are, the elemental equations that are left in your circuit, always with reference to you're in state 1, so look at this diagram, right? And remembering that the diodes are effectively just shorts at this point. We can also do Kvl and Kcl. So there are one Kcl equation and two Kvl equations. Let's reduce this to a differential equation in Vc, starting with the capacitor elemental equation and doing some substitution. Kcl, resistors, so they're elemental equations. Kvl, both 1 and 2. We finally get down to equation 5.5, which is a nice first order equation where the time constant is given in 5.6. Word. So the solution to this familiar differential equation for our initial capacitor voltage, Vc0, input Vs, A sine omega t, is our output Vout. So that is the solution during while we're in that state. Yeah, the other charging state, S2, is similar and yields an alternative formulation of S2, which is to say that S2, the other charging state, occurs when Vs is less than 1.2 minus V out, which I think is a typo. I think it's negative 1.2. Pretty sure. I'm going to go with it, and then if I'm wrong, I'll let you guys know. But I'm pretty sure this is negative. Yeah. Let me just think for just a moment looking at this. So we need to be in this one here. So we got to be able to drop 1.2. Okay. And we got to be able to also drop this. And the negative here is effectively helping us. Okay, so that has to overcome all of that. So it has to be less than so VS has to be less than negative 1.2 minus VL. That is correct. The minus sign should be there. Good. The discharging state S3 is the easiest circuit to analyze. It is simply the capacitor with an initial voltage discharging through the load RL with no forcing. So that's this last circuit, right? That's just this part of the last circuit. So that one's relatively easy. The other two are more involved, but I did most of it for you actually. So good. Due to the nonlinearities, cycles through so multiple cycles through the states may be required before settling into a steady state. This relatively complicated analysis is sometimes bypassed by the method that follows in section 5.1.2, which we'll talk about, a quick and dirty model in just a moment. But it is important to recognize that we've done most of the analysis actually for doing the full circuit analysis. So you could finish that and predict exactly what the voltage should look like for your lab. I'm okay if you use the quick and dirty model too, but you just have to use it well. So no excuse for not using it well at least. Okay. So a full time domain analysis of the circuit is preferable to this quick and dirty model, but this method is a nice way to quickly estimate the results. The DC component of a signal is its average value. Okay, so that's an important fact. We've talked about that, but it may not have hit you quite in the same way. The average value of the signal across the load can be predicted if we know the maximum value of the rectified signal, sans capacitor, AR, and the ripple voltage, delta V out, which is the steady state voltage from the high to low output voltage. Steady state voltage from the high to low output voltage. The maximum value of the rectified signal should be AR, the rectified signal maximum, is equal to the input amplitude minus 2 times 0.6. Okay, so where A is the input amplitude and 0.6 comes from the voltage drop across a diode. So we have two diodes. When you go over to the load and you come back from the load, you get 2 drops. So 2 times 0.6, so 1.2. Then the DC component of the signal should be approximately AR minus the ripple over 2. Okay, so AR is the top of the signal. VO over 2 is the band over which it is going to be essentially bounded. And so then if you divide it by 2 and subtract it, you get to the middle. If we assume the ripple voltage delta V naught is relatively small and the AC signal has a high enough frequency that changes faster than the capacitor, we can assume that the full wave rectifier's output can be approximated by the expression delta V naught equals, delta V out equals IRL over 2FC, where F is the input signal frequency. So it's not a total solution because you do need to find what IRL would be. And my recommendation there would be to find a maximum value because we're going to have a varying current that's going to be applied to the load. So I would just choose the maximum, and that would be the widest range, the ripple range. So you could choose an average as well. That would also be okay, but I think probably max is the best. Okay, that's all I've got here. So this is the idea. You can use this quick and dirty model to do, instead of plotting your predictions, so like, I don't know, input, and then like your output prediction is gonna look like that, like this. Oh god, these are horrible. Essentially a bunch of bumps that tail off. And the idea is that I missed one there too. The idea is that we can find the top of it, which should be AR. We can find the delta V not. That was a little low. It's probably like right there, say. And then if you want to find the DC value, the best one, then that's going to be VDC. So you can just subtract half of the ripple if you want, or you could do a better average if you want to. So that is the idea. So if you just find these three things instead of doing the whole analysis, that's fine. But you can't like predict what the signal is going to do. This stuff that I drew on here would just be your data, and you wouldn't have a theoretical prediction other than the bounds. So it is okay. I said it's acceptable. It's better if you do the whole thing. So, all right, that's all I've got.